Alright, so we're looking at 3 problems here. These are in the slides so you can see them without all this extra if you want to go practice them. Those are tests on Blackboard. This is just applications in 8.7, so we're going to see how to use all the different power series, Taylor, Maclaurin series that we've dealt with, just to answer a couple of different types of problems. So we're going to start with number 1, where I'm going to ask you to evaluate the integral as an infinite series. So looking at this, we might think maybe we could try to do this using techniques that we have from earlier in the class, but instead we're just going to use power series. So the way we do that is we have to break up the integrand into pieces that we can actually get a power series out of. So first thing when I see something like 1 over x is I'm just going to peel that off and deal with the inside first. Because remember, this 1 over x, I can just take that out, I can put it back into the series after, and all that will do is have an effect on the power of the x inside the series itself. So we're going to start, we look in here and we see, okay, we've got e to the x. Well, we know from doing this in class that we can create the Maclaurin series of this, so that's the Taylor series centered at 0. And it just looks like this, x to the n over n factorial. Okay, so then just keep going. E to the x minus 1. Well, what happens when we subtract 1 off of this? Well, one thing we can do if we're not really sure kind of what's going to happen is just look at some of the terms. So I'm going to go back up here and I'm going to look at some of the terms of this. So I'm going to plug 0 into this. That'll give me 1. Then I'll plug 1 in. That'll give me x. Then I'll plug 2 in. That'll give me x squared over 2. Then I'll plug in 3. That'll give me x cubed. Now that's over 3 factorial. This is factorial. Technically that is 0 factorial, 1 factorial, but doesn't matter. We can leave that. Okay, so then e to the x minus 1 will be just subtract 1 off. And so what's going to happen here is the 1 and the 1 are going to cancel, which will just leave you with x plus x squared over 2 factorial plus x cubed over 3 factorial with a bunch of extra stuff here. And so basically all we did was we just took away the first term. So we could rewrite this as n equals 1 to infinity x to the n over n factorial, because all we did was remove the first term. So that's perfectly fine, we can leave it that way. And then we bring in the 1 over x, which, that's 1 over x. You have your series. And so that 1 over x can come into the series, and all that will do is just decrease the exponent here by 1, right? Because I'm going to end up with x to the n over x. And if we use our power rules, that's x to the n minus 1. So this will be equal to n equals 1 to infinity, oops, x to the n minus 1 over n factorial. So there we go. That's the inside of our integrand. And so I'm asking you then to integrate this. So then all together we have this integral. Okay, now remember, anything that does not have an x we can move. So if we're looking through here, we see this has no x in it, this has no x in it. So you don't have to take this step if you're comfortable, just kind of assuming that's what's going to happen and going. But if you want to, you can take the step of moving everything outside that you don't need. And that just leaves you with this inside the integral. And this is something that's easier for us to deal with. We know how to do this. We add 1 to the exponent and divide. So then that should be equal to n equals 1 to infinity. We will add 1 to the exponent. That'll give us x to the n now. We'll divide by that number. We still have our n factorial. And then we've got a plus c out here. Okay, maybe I'll put a little time sign in there so everyone can see it. So there we go. Pretty good. That's all we need to do. Done, done, done. So at this point, you could try, if you really wanted to say like, well, is this a function? Is this power series that of a function that I'm supposed to be aware of? That would be kind of a lot of work to ask you to do, especially on a test. So this is perfectly fine. You stop here, you're good. Okay, so number 2 says use the first 6 terms of the Maclaurin series for e to the x to find an approximation for just e. So let's do that one. Alright, so remember, Maclaurin series means Taylor series at the center of 0, and we actually already have this in our brains, x to the n over n factorial. Okay, so it just says use the first 6 terms, so let's just write them out. We already started doing this. This is 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial. So that's 1, 2, 3, 4, 5, 6 terms. Okay. So let me change this up a little bit. So that's e to the x is approximately that. So it's not perfect because we're not going off to infinity. This is just an approximation. So then e to the 1, which is just e, is approximately, plug in 1s everywhere. And keep going, and keep going. Okay. So let's see if this little math tool is going to work for us. If not, we could just plug it into the calculator. But let's give it a shot. Let's see. Is this going to like us? Aha! Evaluate. And there we go. So just using the first 6 terms of the Maclaurin series, we get that E is approximately 2.71667. That is our approximation. Not bad. Okay, so that was it for 2. So let's go to number 3. So number 3 says, find the sum of the series -1 to the n pi to the 2n plus 1 all over 4 to the 2n plus 1 times 2n plus 1 factorial. So this might look crazy, but we have a bunch of series in our pockets we need to think about. So before we can go any further here, let's rewrite this a little bit. The first thing we should notice is that I've got this power here and this power here, and they're the same. So a good step 1 would be to put everything together that's similar. So -1 to the n, and then we've got pi over 4 to the 2n plus 1, and then we've got 2n plus 1 factorial. Okay, so this should look familiar. We've got odd, so remember 2n plus 1 means odd numbers. We've got a number raised to the 2n plus 1, and then we're dividing by the 2n plus 1 factorial. We've also got the alternating piece. So that should scream to us sine of x. So we did this Maclaurin series before. We look at this and we say, okay, this is sine x, and that's something that if you didn't see that right away, go back, go over how we did e to the x, cos x, and sine x, and make sure you're okay that you kind of see that that's what's happening here. But instead of an x, we don't have an x. We have sine of pi over 4. Well, what is sine of pi over 4? Well, if you don't remember, always go back to your unit circle. There's pi over 4. It's 45 degrees. Little 45 degrees there. And that's root 2 over 2, comma root 2 over 2. And there you go. So that series is equal to root 2 over 2. So that's 3 fairly quick examples where if you can leverage what you know about e to the x sine x as series, you can actually run through these pretty quick. So my advice to you is don't necessarily rely on having to recreate every series every time. There's a table in the book, I can't remember exactly what page it's on, but I put it in the notes, where it gives you a table of all the big ones. Arctan, the natural log, exponential, sine, cosine, just ones that are really helpful if you know them. Now you have the tools to recreate them on the exam, but there's going to be some that if you just have memorized, things will be a lot easier. So I'll post the solutions on Blackboard to this. Feel free to ask any questions if you have them.